Hello everybody, this is Mr. Kusaj. This is the next lesson. It's chapter 1-3, continuity and behavior and limits. So don't forget to put the date there. So continuity and behavior and limits, just like the English words imply, we're talking about a graph. Let me cover this so you don't get too far ahead and get confused. So continuity, we're talking about graphs. So a continuous graph is just that. It continues and there's no interruptions. And behavior, what happens in the end? Does it go up? Does it go down? How does it behave? And limits, sometimes we approach something but we never pass it, just like the English word. There's a limit, but you can't go past it. So first, let's talk about continuous functions. What that means is no breaks, holes, or gaps in the wave, in the graph, right? So here's a graph, and if you look, it's continuous, right? So if you look, say, for this number C, there's something there. Right? For this x, there's a y. For this x, there's a y. For every x, there's a y. That's called continuous. Now, that's different from discontinuous, right? There's three types of those. Basically, I'm going to show you the three pictures, but basically, it's going to be a graph where it's not smooth and unbroken. There'll be gaps or holes or something. So the first one is not continuous, is discontinuous this way, right? Look at this. So if you look, is smooth, continuous all the way that way, continuous all the way that way, but at this number, let's say that number is 2, okay? So C means any number. So let's say it's 2. At 2, it's discontinuous. There's no graph there. For x equals 2, there's nothing there, right? This goes up forever, gets close to 2, but never reaches it. Same thing here. So this is discontinuous. We call this infinite because this goes up, this goes down. They're never ever going to meet. They go infinite opposite directions, right? So this type of discontinuity is called infinite. A second type is called a jump, and just like you would expect, right? Here's the graph. It's going fine, it's going fine, it's going fine, and it's supposed to keep going here if it would have been continuous, but it jumps up and starts over here, right? That's different from here where it goes continuous forever, opposite direction. It's doing fine, except there's a jump here. Okay, so this is discontinuous. So let's say this C means 2. So at 2, there's a value for y here, but there's then it continues to here. Okay, and the third type is called removable, or another way of saying there's a hole there. So if you look, this looks continuous except this one point. So it looks like, oh yeah, for every x, there's a y. For every x, there's a y. For every x, not this x here. Let's say that's 2. Oh, look, when you get to x equals 2, there's nothing there. So this is discontinuous. It's almost continuous, except for one point. Right? So those are the three types that we're going to see. So our job is to check if it's continuous by trying values close to whatever x we choose, right? Close to that on both sides. So if you look at this number here, we check on the right, we check on the left. Yes, everything is there. We come here, we check on the left, it's going down, down, down. We check on the right, it should be down there. Oh, it's not down there, it's up here. So then we know it's not continuous. Okay, so we got to check both sides. And we have some notation. The way we write it is limit of the function as x approaches c. That arrow means gets close to c, right? So we don't want to know what's at c because that would be easy, right? F of c, we could just plug that in. But we want to know about the numbers that are close to it. Let me show you with examples. 2 examples and we're done. Okay, suppose we have this function right here. So I want to know, I don't have the graph for this, I want to know that graph for this, is it continuous at x equals 2? Right? And you want to say, well, why don't you just plug it in? Well, you could do that. You could do that. You could just plug it in. But look, remember our examples? If you plug it in, then it might be this kind of situation where there is a value for 2, but it's not continuous because on the other side, it starts somewhere else. So what we want to do is look at both sides of 2. Look at this. Right? Here's x. X equals 2. So look how we're getting closer and closer and closer to 2 from the left and closer and closer and closer to 2 from the right. So we want to know, are these going to the same point? Are these going to the same value? So if we put all these values in, are they going to the same point? Right? Look at this. Go back to this. Right? If we go from left to right, look, they're not going to the same point. Look, they're not going to the same point. But these are, look, they're going to the same point. So this is continuous. So what about this? Our situation. Is it continuous at 2? Well, let's see. If you plug 1.9 in, 2 times 1.9 squared minus 3 times 1.9 minus 1, it comes out to 0.52. Then 1.99, 2 times 1.99 squared minus 3 times 1.99 minus 1 comes out to 0.95, and so on. So we can see that it's getting close to 9.5, 9.95. The next one will probably be 9.9995. It's getting close to 1. So as we go this way, it's getting close to 1. Should I put 1 there? I don't know. Is this getting close to 1? Right? So you plug in this one, this one, this one. Yes, it is. 1.5, 1.05, 1.0005, 1.00005, 1.00005. So it is getting close to 1. So they're both coming closer and closer to 1. They're approaching 1. Right? So when you do the assignment, you don't have to point out that it approaches 1. You see that it approaches 1 from both sides. So we can say the limit of f of x, our function, as x approaches 2. I'm sorry. Limit of f of x as x approaches 2. What you're saying here is, as we get closer to 2 from both sides, what number are you reaching? And we just found out that we're going for 1. Okay? Now, before we leave this problem, we want to check if f of 2, right? If f of 2 exists. And it should come out to 1, right? Because if you look at this situation, we could have one of these things where you plug in your 1 and there's nothing there, right? So they both look like they're coming close to 1, but what if there's nothing there? So let's check to see if there's something there. Actually check that point. So f of 2, is it equal to 1? So we have 2 squared minus 3 times 2 minus 1. So what is that? 4, 8 minus 6 minus 1, which equals 1. Okay? So what that tells us is that it is continuous, right? It does exist. right? There's something there. We say, yes, f of 2 exists. It's continuous on both sides. So we got a perfect, So we got a perfect graph here, a perfectly continuous graph. Okay? Let's do the second and last example. Nope, that's the original. The second example is f of x equals x plus 3 over x squared minus 9. Is it continuous at x equals 3? Okay? So, we set up the chart, 3's in the middle, and then do 3 very close on the left and 3 very close on the right. So, 2.999, 2.99, 2.9, that's good enough. 3.001, 3.01, 3.1, that's good enough. You plug all these numbers in and you get this. Okay? You can pause and copy it if you want. Now, or you can just listen and copy later. Notice what's happening here. As we're getting close to 3 from the left, we're going further and further down. Right? You see that? Further and further down. As we get close to 3 from the right, we're getting further and further up. So they're going like this, which is, if you recall, this situation. So definitely not continuous. Right? Definitely not continuous. So because we approach different value, right? We're approaching negative 1,000, 1 million here. We're negative infinity here. Positive infinity here. We're approaching different values from each side. We're supposed to come together, but we're going different directions. That's why it does not exist. The limit of f of x as x approaches 3 does not exist, so we say it's discontinuous. It's not continuous. It's discontinuous. Okay? Should we check if f of 3 exists? Should we check if f of 3 exists? It doesn't matter. It won't. But the question was, is it discontinuous or continuous? And we found out that it's discontinuous. So you could plug it in, and by the way, you'll get a 0 on the bottom, which means it doesn't exist. But we're done. We don't have to check f of 3. Okay, so can I leave you with 2 try problems? So here, the 0 is in the middle, so you approach 0 from both sides. Same thing here. So is it continuous at x equals 0? Is this function, look how small these functions are compared to the 2 I gave you up there. Are they continuous at x equals 0? So set up the chart. That's the least you can do, is set up the chart with 0 in the middle and some numbers to the left, some numbers to the right, and see if it's approaching the same number. That's our job, to see if it's approaching the same number. Okay, under 14 minutes, that's pretty good. All right, see you next time for part 2. Bye.